Okay, so this paper is on Canopy, which is a end-to-end performance and tracing, end-to-end performance tracing and analysis system. So this is presented in the Symposium for Operating System Principles in 2017. Yeah,
Mm.
and Canopy is a collaboration between Facebook and Brown University. So actually only Jonathan Mace here is from Brown and everybody else is part of Facebook research.
Mm. Okay,
Yeah.
so I may have some background here. So so this year's work is more about the debugging. When we saw debugging, is more like about the causality analysis to understand how the system really works. So sometimes when we run a system, the program executes and some phenomena happens. And there are a lot of approach to inventing some black box approach. For example, the approach using statistical analysis approach to infer where the problem is. But anyway, when the program is running, there's always a cause and effect. So in this approach, this Canopy approach it has been deployed in Facebook. They're trying to understand what the system, what events and what the really things is, what really is going on, and to analyzing and explain something. Of course, for example, the Xianglin's work or even the Rockman's work, there's a lot of approach we design is trying to explain something. We not only to recommend some, for example, some fishing website. We are not no, we sometimes we not only want to just infer where the bird is, we also want to explain it. And actually, the trace analysis is a very important infrastructure for us to fully understand what's really going on, because the trace actually record everything during execution. So we would like to build the cause and effect collating information along the trace, so that based on the trace informations, we can ask questions and answers. For example, when some event happens, for example, a bug happens or exception happens, we can base on the trace information and trace back to how the effects is propagated along the execution through the cause and effect. The causality chain is here. So the Canopy is one infrastructure deployed by Facebook here. And I think so this work is somehow related to a lot of the research areas in our group. Mm.
Mm.
Okay, Yuchen, please go on.
Okay. Right. So Canopy is Facebook's end-to-end performance tracing infrastructure. So it will record events all the way from the request start, which is like mobile applications or browsers, and all the way to the backend services. So Canopy is mainly motivated by the fact that, like, if you want to trace a certain service, right? Because Facebook's backend is very distributed, and if you try to instrument one part, it will like you will only be able to like get the trace data from that part. And if you want to like instrument some backend service, then it will only be you only obtain data from the backend service, and there's no way to like link the two. So previously, Facebook engineers would have to learn like both the services and the execution model and the instrumentation in order to be able to like gather like information about the whole end-to-end process. So that's where Canopy comes in. So Canopy is meant to be able to like complete the pipeline all the way from the start to the end. Yeah. So these are some of the features of Canopy. They decouple the design for tracing, and it separates the instrumentation from the trace model. So when the instrumentation is run, right, we'll be able to log certain events, and all the events will be able, like, they will translate it into a trace model, which is later used for like all the queries and exploratory analysis. So they separate it in order for the instrumentation and the trace model to be extensible independently. Yeah. And they provide a complete pipeline to transform traces into a custom set of extracted features. And they also provides a set of customizable tracing components, which allow you to make multiple views of the same data. Okay.
So given that there's multiple view of the data, so do they provide any UI, the GUI component in the paper?
Yes, there's one screenshot of the UI component.
So you will mention this in the screenshot later, right? In your presentation later.
Oh, actually, I didn't include the screenshot, but
Mm.
the UI itself, like, I think I can show you lah. I'll just show later.
Yeah, you can share the so here, or maybe you can go on later, but I really care about the trace analysis and the visualize the trace or visualize the advanced data. So that's really interesting. Okay, keep going.
Okay, so later on we'll build on to their model, their model construction. So, and then after that, I think the UI would make more sense. Okay, but anyway, so there are some challenges with respect to implementing Canopy. One is modeling the trace data. So when they collect the trace, they are logging certain events, right? But we cannot expose these events to like the query later on. Yeah, because the events are too finely granular. So it's computationally infeasible to like run queries on events.
So maybe I can help explain a little bit so that the other student can catch a little bit. So I'm not sure whether you can fully grasp it. So the problem settings. So by the way, Yuchen, do you have the slides for specifying what problem you're going to be solving? So is there slides for that, or you can just you just mention the challenges?
Oh, this is part of the problems. Yeah.
Problems. Maybe I can emphasize a little bit. So for example, in a distributed system, there have many nodes here. So I'm not good at drawing. So suppose we have multiple system here. For example, in our own lab, we have already a distributed systems for crawling and detecting phishing website. So for example, there are some nodes are supposed to be a master. So I'm not sure whether you are familiar with the structure of the master and slave structures. So sometimes when we have distributed systems, we have multiple computers, and these computers work together to finish one task. And the separate task is usually deployed on different nodes in the system. So there somehow makes a communication here. So this here the problem settings. So when the distributed system is deployed, so the interaction between different nodes are very complicated. Sometimes many events they happen simultaneously, and also the messages communicated between the nodes here will still using some callback mechanisms. So the problem here is that when there's something unexpected or when some unexpected event happens during the distributed systems, and how would we quickly identify the problem, what this problem is? So this is more like a system and a software engineering problems. And the solution in this work is going to building a trace, just like Yuchen just mentioned. So when the many nodes are running, so when the programs are running on different nodes, and record the execution trace of each node. So then they will build a model called a trace model. The trace model will executing all the past events or all the recorded events of those nodes, right? So now we will have, so that means that we still have a database. This database is supposed to be a trace database, right? In such a trace database, when the execution information of such a distributed system will be recorded on such a trace. So when such happens, when such a data happens, we can analyzing the bug. So the idea is more like when there's something happens, or when the bug happens or an unexpected event happens, the debugging process has been transformed or converted into a problem of finding the first buggy steps on the trace. So now Yuchen is looking to, if we want to have such a solutions, and what kind of challenges do we have? For example, how do we modeling the trace data and how do we analyze the data and and how the data can support different use cases. So that's the overall idea of this paper. Okay.
Yep.
Yuchen, do you have any comments on explanations or just keep going on?
I don't really have any comments.
Okay.
So yeah, so like I said, the events itself, we cannot present this to the user of Canopy because these are too like low level detail, and you will require the user to reconstruct like the whole execution and what's happening from the events, which is like that's not what they want to do. Yeah. And on the other hand, if we model the trace data with like a high level primitive, then this stops being general because there are certain execution models that cannot be represented. So one of the examples that they give is a span. So span is what this system called Dapper uses. Dapper is used in Google for distributed logging. So what Dapper does is they represent executions as like blocks, and each block like it makes a call to other blocks. So the execution model will look something like this. Yeah, so let's say that this is a thread, and then it runs a certain program, and then this program makes an asynchronous call to another thread, for example. So this is one way to represent a trace. But the problem with this is that there are certain execution models that cannot be represented like this. For example, event loops and queues. Yeah.
So event loops, why the event loops cannot be represented like this? So what can you have a definition of the primitives? So what do you mean by, so how do you define the high level and the low level primitives?
Right. So I'm guessing the high level primitives means some semantic representation of an execution. So in this case, the lowest level is like an event, right? We can go with events. But like we said, the events are too fine granular and we don't want to store everything as events, right? So on the other hand, so we need to form some representation of a trace that is like not events, and then it has to, and it can't be expressed any more simpler. That's why it's a primitive, right? So, but once we raise this abstraction level up, then it fails to capture like certain behaviors that the Facebook engineers would want. Yeah.
Also, the system will have to be general, right? We need to build a general system which can record the trace executions of a lot of systems instead of one system, right?
Yeah, exactly. Yeah. So for example, like one part of the Facebook stack might be able to be represented like this, but maybe another part cannot. So there's no one size fit all solution. So we cannot have a high level primitive. Yeah, does that make sense?
Yeah.
Okay. All right. Okay. So that's the part of like data collection. And for analyzing the data, so later on we'll see that the data, the traces, right, they are transformed into some data set, which is like it encapsulates certain features of the trace. And the reason for that is because they don't want to expose the trace by itself as like an element in the table, because it becomes very hard to query over all these traces because there's a lot of traces and a lot of events in each trace. And another thing is also because it's hard to write a query for the trace. You probably want some abstraction over it so that it's easier to write a query.
So it depends on what query you want to have. So for example, if we want to have a query like when certain variable is written or when the exception will happen, so that is not a difficult query to analysis, right?
Yes, but I believe that you can make it faster by only keeping like perhaps all the exceptions of that trace rather than the whole trace itself. Yeah, which is what they are going for, I think. So yeah, And then another thing is to be able to support multiple use cases. So
The question, because we still want to build the trace recording technique. So we still have a trace, but our trace framework is not for the distributed system. It is for Java program execution. So we still are building, as you tried before, you still try to record the execution trace into the circulated database, right? So it seems that as long as the schema just here, but of course, just as I mentioned in these slides, you mentioned that sometimes maybe all problems of the tracing might be that our events is too fine-grained. So maybe we require too much information. It is possible. But what I'm curious about is that how, and since because we still have such a need, so I didn't see. So as long as there's the structure and schema of the trace has been defined, there's always a way to define a query, right?
Yeah. Yeah.
That's the thing that problem. The amount of information encoding the trace is too large. For example, it may include millions or billions of trace steps. So that becomes more computationally expensive.
Yep. So later on, we'll see that the way that Canopy does it is that they allow for like anything. So if you do need all the steps in the trace, it's also possible, and there are ways that you can go in and change how you want the data. Okay, yeah. So that's the part about supporting multiple use cases as well. So a lot of each step in the Canopy pipeline is extensible. You can go in and configure as like however you want. Okay, so this is the rough design of Canopy. There's a front end and a back end. And for the front end, so what happens is that Canopy exposes instrumentation APIs for the engineers to use. And the engineers will simply instrument their system components to record performance information. So an incoming request will have a trace ID generated. And then this trace ID is propagated along the execution path. And then the Canopy runtime itself will generate all these events, and then it will be sent to this backend to be aggregated and processed. So in the backend, it's called a tailor. And so what it does is that they will aggregate all the events in memory first, but they will also persist it into persistent storage. So all the raw events are stored, and then they are sent to this queue for processing. And then in the processing, they turn from a trace to a trace model. And then from the trace model, you can apply feature extraction lambdas to get the feature out of the trace. And all those like extracted features, right, are then like stored as a trace data set to be used in querying and visualization and graphs.
Yeah. So here the question. So how to transform? Do they mention that so the feature extraction and so from your day flows, we start from the raw trace events, right? So there, of course, I have a few questions, but maybe some of the questions will be addressed later in your later slides. But for here, when we have the raw events, so I'm asking for these two dotted lines. So when the raw events will be, why the raw events will be still used in the query results visualizations? Because the raw events will be translated into a trace data set, right?
Yes. Okay.
So let me make my questions more specific. So what kind of feature and why the feature is called the feature lambdas? So what does the feature, can you have a few examples of such a feature? And the model constructions, is there any schema or mental model of the model structure or the constructed model?
Okay, so they did not really give a specific like way. I think they give some clues, but like not very concrete. But I'll try to show you some later. Okay, but so one thing that happens here is that this raw trace events is part of like a load shedding mechanism in order to balance out the the workload when there's suddenly a high traffic. So what happens is that some of these raw trace events, right, they they were split into two paths, right? So they will go into a in-cache memory, and then they are also stored in persistent storage. And so the traces, the events that live in the cache, they expire after a few minutes. So once they expire, right, the model constructor would have to draw from the persistent storage in order to create the trace. Sorry, yeah, to create the trace model. So that's where the first dotted line comes from. And then one of the other features that Canopy allows is that they let you go back and analyze historic data. So so in the end, right, you can still access like the individual models. So yeah, so they let you skip all this step when you want to go in depth and look at exactly what happens. And there's a second dotted line.
It's better that you can have some more concrete data but this is a very good overviews. But in our design, so when you are reporting this idea, I still try to keep in contrast and compare their designs with our own solutions. So we do not have
Okay.
such a the problem. So when we have we are building a database to reporting the trace events. But for those trace events, we do not need to further translate. In our designs, the raw trace events are just as a trace basin, right?
Yeah.
They're just the same data sets, and we do not have such things like the feature limiter and the feature extractions. Okay, you can keep going on. Let me think about it. So I still need to see the necessity and what's the difference between and what kind of additional feature do we want to extract it, especially for the raw trace event, how raw it is, and why they cannot be directly used by the queries.
Okay. Um, Let me see. So let me try to find some example of feature lambda. So that's one point that I haven't talked about yet. So the feature lambda is a feature lambda because it's stateless and it's just supposed to be applied to the trace model. So some example is like these. Let's say like to calculate the latency. So you will take some display done, perhaps it's a component, then it will find all the timestamps and then it will subtract the start from the end. So that's an example of a feature lambda. So these feature lambdas are done in a domain-specific language.
So for example, so their trace is they almost using a kind of languages to describe the trace, right?
To Not really. This is like for the lambda, the feature extraction.
Got it. So for example, when you are having a trace, when some trace happen before and some trace happen after. So when you want to have some feature like a latency, you still need to have a way to aggregate it from the raw trace events. Okay, that's okay. We keep going on.
Okay. Right. And the Canopy provides shared data sets and visualizations. So part of the feature lambda is that they also specify where the process data goes to. So they have different data sets for different features that they extract. Yeah, but small detail there. Okay. So now this part's about the instrumentation API for Canopy. So basically, all it does is it only okay. So they have three functions, right? Which is to propagate the trace ID alongside the request, and then it records the request structure, like when it executes, and then the causality between threads and network communication, and then it also logs certain like performance counters or stack traces. But the way that it's exposed to the engineers is that they only allow you to like set set point a certain statement, and then like they let you measure a function. So this is like the example that they gave for the instrumentation library in PHP.
Mm.
So you can
Can
see
go back
that
to the previous slide. Can we go back to the previous slide? So when using the canopies, the tool of canopies, whether the program, the subject programs will be aware of there will be a canopy, whether will be aware of it or not.
whether they will be aware of it.
The point is that this is a program. So this is a program. This is the subject program LFP, and this canopy, right? C, right? So
Yeah.
when this program is running, so you're talking about instrumentation API, right? So, oh, by the way, let's explain a bit about what is instrumentation. The instrumentation is a way to change the runtime program information, or more like we insert some additional code into specific programs so that we can know the behavior or the runtime information of the program. For example, when a program like A equals B plus one and B and print something and do something, and B equals C equals A plus B, etc. Giving such a programs, and if we want to know, for example, if we want to know how long does the program take a program to executing certain statement or certain instructions, we somehow need to insert. Let's record that this is time one, this record this time two, and then we output time two minus time one, so we can know the runtime execution, the runtime overhead of to explain this statement. And if we have, but if the program itself, we cannot know these. But if we want to know these informations, we need to additionally insert this kind of the statements. When we have this kind of statements, we somehow know the runtime information. So that means when the program is loading, we will insert additional instruction into the programs. So that is called instrumentation. Such a behavior is called a calling instrumentation. Okay. So now let me come back to my original questions. So my question is that when a program is running, where the Canopy systems, where the programmers of these programs will need to aware of that there was supposed to be a Canopy framework to run to monitor this program. Do we need to aware of that information, or the Canopy program will automatically analyze the structure or the runtime information of the program?
I believe it's the former, because on the paper mentioned that a lot of these logging is application level, so they don't actually like analyze and go into like the compilation or the lower level stuff. I believe like the programmers have to manually insert.
That means if we want to use Canopy systems, the programmers of the service system have to call the API of Canopy.
Yup. I believe that's the case, like from what I'm reading.
Yeah, because for our framework, we do not have such a requirement, right?
Indeed.
Yeah, when the program is running, the Java programmers do not necessarily need to know whether it needs to be instrumented or not. We just run programs and take and record everything. Okay, please go on.
Yeah. Okay. So I was saying that the exposed API is actually very small. They don't actually like have a lot of functionality like given to the programmer. So other than these two, there are like different library in different languages, and those different libraries might also have these functions, which is to enable the user to write their own counters and then enable, disable stack trace, capture OS level information. So that's part of other libraries in other languages, but mainly the Canopy itself doesn't expose much. Okay, so these are what the Canopy events look like. So Canopy uses sequence numbers and timestamps to order the events within the same process. And then they also generate a random ID in order to, let's say that you're like making an RPC call, then you will generate the event ID and then you propagate both the trace ID and event ID to the receiver so that you can link these two events together. Yeah. Okay, so the trace model has 4 parts. It's they're described in terms of execution units, which are these high-level computational tasks that is approximately equal to a thread of execution. And then there are blocks, which are segments of computation. So that actually looks a lot like the span that I was talking about. And then there are points.
How do you define the execution unit?
I believe it's basically the like one whole thread, all its operations. When the request starts, that's one execution.
What is the metadata or the schema of the trace looks like? So in a specific structure, so you can see. So here you can see, given the trace, it consists of set of the execution unit, right? And there's different level, right? So the most low level unit is called execution units. Then it's going to blocks, and the blocks, then points and edges. Okay, maybe you can keep going on. I do not interrupt you.
Okay, the most low level thing is like events, I guess, and then it's from the events then they generate this kind of execution blocks and points and edges. Yeah. Unfortunately, they don't give exactly how it's translated. So I'm guessing like you have to manually code out the logic where like perhaps this trace ID and this trace ID, and then like you compare the timestamp and stuff like that.
And how many types of edges are there?
How many types of edges?
Yeah.
I think it's like it can be as many as you want. It's fully user defined.
Fully user defined.
Yeah, so perhaps like an RPC call is one kind of edge, and then like maybe I don't know, some other kind of request is another kind of edge. Yeah. Or yeah. And you know, like how there was queues. So maybe perhaps like the pub sub kind of communication model, then like one publication and one poll, like those can be also linked by an edge.
Okay.
Yeah. Right. So this is just a simple model of the trace. And then if you look at the paper, you realize that like it changes a lot. So at first they define it like this, which is this CS stands for client send. So it sends some message to this other block, right? Then this starts the uh, something receive, server receive, right? Server receive event, and then so it will model it like this. But then they realized that perhaps that there can be more information when to log, such as like when the client is waiting for reply from the server, and then that's when the model will change again to like reflect all this increased need, change in need. So yeah. Okay, so trace data set. So the data set is like the final output that Canopy gives to the user, right? So a trace derived data set is Canopy's high level output. So each row of the data set corresponds to some element in the trace. So what this element is it can be like different components of the application, and yeah, and then they are tied to the trace in that column. So for example, for a high level data set, we can have one row per trace, and then each row has features of the trace, which is like, it can be aggregate statistics like latency, country of origin, browser type, for example.
So here, I think you did good from the very beginnings, but I still have a little puzzle. I'm a little puzzled about how the trace is defined. You can say the trace have elements. So what kind of elements is better that we can have metadata or the models of how the trace model looks like, right? So here I think a lot of information. Okay, at least I know that the trace will have some block, and the block will have some events, and some event, and what kind of how many types of events are there, right? So I'm just puzzled about all those kind of information, and the trace for me is still a very vague concept. Is it better? Is it better to have a more specific model like this, right?
Indeed, yeah. So the problem of the paper is that they did not really give any specifics. So so events have a certain type over here, and this type basically changes as the requirement of Canopy changes. So yeah, so right now there are 21 types, but as they say, it's like extensible and it can go up. So a lot of this is like, it's all changeable. A lot of every single like any facet of Canopy is like extensible, which is both good, but it also means that we don't have a clear picture of like an example trace model, right? For example, yeah. Okay, so implementation. So this talks about, I guess this is more about the back end of how the whole like the transformation into the trace models happens. So when you start a trace, it actually has to require a token from the distributed token bucket. So this is a way to basically rate limit the amount of tracing that you do. Yeah. So what happens is that you must first acquire a token from the bucket, and then they also allow users to control, like one more control over the token bucket. For example, like if you only use the token bucket, then perhaps certain low query per second API calls would not be sampled by the Canopy. So the Canopy also allows you to write certain sampling policies that tell you which traces you should sample from. So a sample policy contains the owner, the sampling strategy, the restraints, and the lifetime, and the level of detail to record. So a sampling strategy can be something like the probability. Let's say that for every trace that comes, maybe I only select 50% of that. That's like possible. Or it can be a rate. So maybe every three, I don't, something like that lah. They also didn't really give specifics for this. Okay, so the restraints that the request must satisfy are things like whether it comes from a specific endpoint, which data center is trying to access, which region it's from, this kind of thing. And yeah, so the level of detail to record tells Canopy like what's how deep a stack trace they should probably record and stuff like that. So Canopy also allows the users to mark a code path as being reached. So this can also be used as a restraint for whether the request should be traced. Yeah. So for web and mobile requests, they will pass through the sampling policies first before acquiring the token bucket. Yeah.
Sorry, can you wait me for 5 minutes? I need to go and handle something. It'll be 5 minutes. In 5 minutes.
Okay.
Please.
Okay. So just now, like I said, the web and mobile requests must pass through the sampling policies first before they acquire a token.
Okay, can you be more specific about the sampling policy? So it's the sampling is about the sampling. So what is targeted for sampling? Sampling for trace or the sampling for the trace event?
Yes. So there's a lot of requests, right? And then we only want some of the requests to be traced because there are a lot of requests. So this one,
they only care about the communication or interaction between multiple nodes, but they don't care about what inside the nodes, right?
they do because
They also care about the events inside each node.
yeah, so like all the processes in the browser, it's part of the trace that is logged by the Canopy. Yeah.
Okay.
Okay. So yeah, so some requests they want to keep and some they don't. So it's defined by the sampling policies. One thing to note is that the distributed token bucket actually there's a separate one from each tenant, and the tenant as defined by Canopy is like whether it's web or mobile. Yeah. So okay, so the local there's a daemon called the configurator that manages the sampling policy and the distributed token bucket. So once they pass, and then Canopy will start logging all the events, and then when they're finished logging, they are pushed to Scribe, which is a distributed messaging system. Okay, so there's also a separate mechanism which is opportunistic tracing. Because in some cases, we don't know whether the sampling policy passes until partway through the request. And what it will do is that the client will just store the trace first, and then once the decision comes back, then the client decides whether to send it all to the server or to delete it.
Why is called opportunistic tracing?
It's opportunistic because they start storing regardless of whether this outcome is true or false. So
what kind of outcome?
What kind of outcome? Oh, so it's possible that they like this request might not pass the sampling policy because this restraint we don't know what the result of it until only partway through. Yeah, so we just start recording first. Yeah, so when it comes back, then we decide whether to keep or throw away.
So can you reason the input, right? In what kind of scenarios do we need to start recording anyways and then just straight away?
Okay. I think it's possible to say like maybe this request is accessing a certain data center, right? And we don't know the final endpoint, like where this request is going to draw the data from until it reaches the server, perhaps. Yeah. So I might restrict that as a restraint, but we don't know whether this request fulfills the restraint until it reaches the server at least.
I see.
Yeah. Okay, then now this part is the backend, the tailor. Okay, so the tailor is made up of a few parts. We'll go into the details, but since this picture is quite big, so it won't come out later, right? So the first thing that happens is that we pull the events from the scribe system. So there will be a pool of fetcher threads that keep asking for the events. And it will be immediately written to persistent storage and inserted into a in-memory cache. So we are at this part. So the processors will ask for events, and then they will send it to the database, which is HBase in this case, and also kept in in-memory cache. And this in-memory cache will expire in 15 minutes. So this is also part of like the load balancing scheme, because some requests might take very long, like especially if the client is very outdated or like a super old phone. So it's possible that like not all the events come in. Yeah. So after a while,
the HBase, all the stuff in the HBase is a raw database, right? Or the raw trace, or the raw trace data set.
yes, I believe HBase stores all the events.
I mean the raw events.
Yeah, raw events. Yeah. Okay, so after all the events come in, then the fetchers will evaluate a set of triggers for determining whether that trace is completed. So the triggers is also like user implemented. It can be things like 10 minutes after the start event, or 15 minutes since the last poll from the database, something like that. So all of these will be evaluated, and if it passes the trigger, then it will be sent to be converted into the model, the trace model. And in the case that the events received later, then the triggers are evaluated again. But apparently this is it's a okay trade-off, because it only happens less than 0.03% of the time. All right, so for each pair, they will retrieve all the events from cache. So if the events are expired, then the trace is enqueued to the delayed extractors. The delayed extractor is basically the same as a tailor, but they will retrieve the events from persistent storage rather than the cache. So it's this part.
So here's a question. So on why the cache? What's the purpose of have such an in-memory cache?
Right, because they want the whole system to be very responsive and real time. Yeah, so putting it in memory will make it faster, but
so here is the offline decision. Everything is offline for the tailor, because we're talking about the backend, right? So when
Yep.
the backend, so we learned that a lot of during the fetcher, the poll events, and everything has been reported. When every raw event has been recorded in HBase. So when everything is recorded, so what is use case here, or what is the scenarios here? You're talking about the scenarios of recording trace, or you're talking about we're using the trace now.
We are using the trace, yeah. So
Okay.
the events will come in concurrently, right? But the way that they define whether a trace is completed, because it's possible that some events are just lost, and then we don't know whether they are coming in or not. So that's where
really the two scenarios that happen simultaneously. You just as you said, the trace are just coming concurrently, so that the trace recording is always happening, right? That means the database is still always keep growing. But in the meantime, the programmers or the software engineers are now trying to visualize and to analyzing the recorded trace now.
Sorry, so what's the question?
I mean the two scenarios are happening simultaneously. One scenario is of the trace recording scenarios, and one scenario is that the users or the software engineers are now using the trace. These two scenarios will happen simultaneously.
Yes.
Okay, yeah. And this in-memory cache stores the most fresh data or the most fresh events.
Yeah.
or the most frequently used events?
Most fresh. So they order by, sorry, so they keep like all the trace IDs, and then every time the event of a trace ID comes in, then the timer refreshes. So yeah, and then the timer expires after 15 minutes.
I see. I see. That means if the users want to curate certain events, they will first search the in-memory cache, and if cannot find it, they go to the HBase.
The user does not come in until all the way at the end. So at this stage, there's no user interaction.
Okay, I see.
Yeah. Yeah. So the triggers basically tell when the triggers decide when like the trace has completed, and then it will be passed into the builder. Yeah. Okay. So the builder will inspect the type of the event, and then it will delegate it to event handler. And once again, like the paper does not provide any details as to how the event handler will handle the event. But apparently, so after this event has been handled, the builder will once again go through the trace and handle incomplete model elements and correct errors and infer additional elements and things like that. Yeah. Align timestamps.
This is quite an engineering paper, but I can see the huge amount of effort behind the paper.
Yeah, I agree. This is very engineering like. So then the builders will run one final pass to annotate all the elements, and if it's broken, it will annotate it so that the Canopy engineers will come and fix the model or instrumentation. Okay, feature extraction. So now we are at this part of the pipeline. So the features come bundled with the dataset configuration. So first there's filtering, and then we extract the feature, and then the config also tells you like where the extracted feature and the dataset goes to. So after that's done, it's enqueued into this thing called the isolation queues. And then some extractor will pull this queue for traces using some this algorithm called the deficit round robin. So I guess what's happening here is also like another mechanism for load balancing. So basically all the models will come in here, and then it will be taken out to be transferred to the final database that users use to query. Yeah. Okay. So these are some notes from the authors about scalability. So because the traces, right, they shard it by trace ID. And since Canopy itself is also distributed, so if you want to scale Canopy, you just need to provide more machines. And the number of events per trace will increase as the instrumentation matures. So Canopy allows for multiple levels of trace details. So it's not necessary to extract all the number of all the events every trace. And one thing that the users notice is also that the feature lambdas, they're not very expressive because of the limitations of their DSL. So Canopy provides IPython integration. Okay, so this is some of the results from this is the overheads from
All right, so I think we can skip the evaluation overhead. What we care about is user scenarios. So does the paper present and case studies or user scenarios for this work?
Yeah, okay, so case studies, there's some case studies. One is that, for example, you can extract the critical path from all the traces. So it will look like this, and then Canopy will then suggest
And how do
this.
they define the critical path?
The critical path is basically the longest execution. Well, basically like how long it takes for the whole program to execute.
Mm.
Yeah. So the exact feature lambda, I don't have it, but it's possible from their DSL. And basically this shows that these are all the blocking executions in this request, right? So this block must complete first before this thread can continue. And what they notice is that this is not supposed to happen. So by right, this block, suggestions block, is not a it's not an important element to show on the Facebook page. And what should happen is that like after this execution block finishes, the server should start pushing things to render on the client already, but it's not happening. So Facebook engineers are able to identify that, oh, there's a problem here, and then it has to do with the server execution environment. It's not, and it's like different from the code itself, which is why there was this regression.
Yeah, and how about so here? So you also mentioned there the causal relation between the events. So in these scenarios, and how do we now? So given the events that such a delay happens, what kind of the causal events can they rely on, or any other clue can they further investigating the root cause of such a delay?
What kind of clues?
Yeah,
I guess a lot of it is ad hoc because like they said, it's a lot of like just human experimentation. So they first notice that there's a latency, and then they go in and then they look at some trace data, and then they see that okay, for a subset of requests, this thing happens. And then they go into pinpoint like, okay, so there's something wrong here, and then they go and debug.
Okay.
Yeah.
So here is more. So the whole tool of Canopy is still a very high level point of view. Very high level point of view. So they just prevent. They just provide such a. I understand that it's very sophisticated systems to behind, but on evaluating its usefulness, they are just showing their runtime performance, right? So is there any case studies here?
Case studies that show runtime performance.
The case studies for shows the usefulness of the system.
The usefulness of the system. The usefulness of the system. I feel that there isn't. It's really more about the capability of like what is possible with Canopy, rather than like that is the usefulness. So the users can basically write their own feature lambdas. But one thing that the researchers also notice is that in the end, they are all using the same features, right? A lot of it basically links latency and some other feature together, and that's how they do their analysis. Yeah, so I guess
the end of the the end of your presentation?
Yeah, so other than case studies, there's they mentioned some related work, some other like distributed performance analyzing systems. Yeah. Then other than that, that's all.
Okay, so we'll go back to the evaluation part.
Evaluation.
Yeah, so for here, for this evaluation, it's all about the performance, right? The latency. That means that it only the point is that the whole Canopy systems only increase a very limited overhead, incur very limited overhead, and so that's all its evaluation.
Yeah, yeah. For their evaluation, they just talked about the overhead, and um, actually, I don't really understand how the numbers are not monotonic, but they just mentioned the mean, and then they said that, well, most of it is under 10%, so it's good.
Okay. Okay, thanks, Yuchen. So let's talk more about our own trading systems. I think eventually our approach will go for distributed systems, but for currently we are only want to extend our tracing system into concurrent systems. And I think you have finished your task, right? You have committed all your coding to the GitHub.
Yeah.
Okay, so maybe next week I'll organize a meeting with you. Maybe the next Wednesday. Okay, thanks, Yuchen.
All right, sure, no problem.
Okay, so next one, how about Xianglin?
Okay. Yeah, so this paper is called Empirical Study of the Topology and Geometry of Deep Networks. It was published in CVPR in 2018. So nearly all of the author works on computer vision and machine learning research area. The first author is a research scientist in Google DeepMind. So basically the background, the geometry of classification regions and decision boundaries induced by traditional classifier, such as linear regression or kernel SVM is fairly well understood. However, for the deep neural network, the geometry properties of classification regions and decision boundaries still receive little attention. So basically in this paper, they try to address this problem by investigating the geometric properties of classification regions and decision boundaries. Specifically, they view classification regions as topological space and show that the classification regions are connected for each class. And then they view decision boundaries as hypersurfaces and show that the decision boundaries is flat in most directions, with only a few that are significantly curved. And in the last, they leverage those properties to improve the robustness of classifier to adversarial attacks. So later we will talk about more details. So a little bit terminology and notations in this paper. A L class classifier is denoted as F, which map a input from D-dimensional space to L dimension space. So D denoted the input dimension. And then an estimated label K or prediction for any input x0 is denoted as K hat x0. And classification regions is denoted as R1 to RL. And then for the decision boundary between class I and class J, is a set of points which meet the requirement that Fiz minus Fjz equals to 0. So that's the definition for the boundary. And the last one is the minimum perturbation. So
okay,
for
our case is a little bit different, right? Our one is that Fc is smaller. In our approach, for our deep view inside approach, the absolute value, our definition of boundary is that the absolute value of Fc is smaller than epsilon, right?
Yeah. But here they defined it as 0. And the minimum perturbation for any given input x they try to find the R that can, when X plus this perturbation, the labels would change.
The minimal motivation. Okay.
Yeah. So to investigate the topology of classification regions, first they propose a question: do deep networks create disconnected regions, or disconnected regions like the image on the right, or one large connected region per label, like the image on the left? To formally define this, they assume that when given two data points from the same RI or have the same label, not have the same prediction, and that's a continuous curve exists such that there's a path between these 2 points, x1 and x2, that this path is included in the classification region. And they assume that if this path exists for any 2 points, then the classification region is one large connected component for each class.
Hey, by the way, for your pictures in the left, so if the classifications looks like the pictures in the left, so the blue ones, right? The blue ones, so the blue point is still the blue points are still disconnected, right? The blue parts. So that means, so in your picture, there's a binary classification. The blue.
I think they just show the red
idea, right?
because it's in the 2-dimensional space. However, if it's in a high-dimensional space, then the blue part might still be connected. It's just an illustration.
But if we project from a high-dimensional space into low-dimensional space, if we would like to make such a projection, there's still if you're such a state the arguments or the hypothesis that the connected classification regions is true, it means that if we project all the stuff, all the classification boundaries, all the classification regions into the 2-dimensional space, and all the regions supposed to be connected, right?
Yeah.
The regions for a single class.
Yeah.
Okay.
Yeah. And then they propose an algorithm. If we can find a path between any 2 points from the same class, such that only anchor points in between still inside the same region, then they can claim that they find a path for the x1 and x2. So that's the basic idea. And the path-finding algorithm looks like this. It's a recursive process. First, when we are given 2 points, x1 and x2, we first find the midpoint, which is x1 plus x2 divided by 2, and then check the prediction for xm. And if xm is inside the classification region, then that's the best. If not, they find the minimum perturbation to project xm back into the classification region of x1 and x2. And after that, they can add xm to path. Now we have path x1, xm, x2. And then we do the same procedure recursively to x1, xm, and xm, x2 until the distance between any 2 consecutive points is 4 orders of magnitude smaller than the distance between.
What do you mean by the 4 orders? The 4 orders of magnitude?
Oh, for example, if the distance between original 2 images is 1, then they set a threshold, which is 10 to the power of -4. So basically they set a threshold, and if the distance between any two consecutive points is below that threshold, then they stop.
See.
Mm.
So by the way, so here so there's one scenario that is when xm is the middle point between x1 and x2, right?
Mhm.
So if xm is equal to the label of xi, then the evidence
or you mean x1 and
because the label of xi, x1, x2
Mm.
is the same, right? So I'm
Yeah,
saying
Mm.
xm, and if the label or the predicted label
Mm.
xm is equal to that of x1, then the evidence stop.
Not stop. They yeah, they
If I remember correctly, you're saying that if xm is have a predicted label, have a same predicted label of with x1, then you say it's perfect, and then stop, or the
not
evidence.
stop. No, they add xm to the path.
Okay,
If not, they add a perturbation so that xm still have the same label.
I got it.
But the stop requirement is the distance between 2 points is
And
below.
okay, the recursive happens because in the next round, the recursive happens for x1, xm, and xm and x2.
Yeah.
Until they find the distance between x1, xn, or two consecutive xi and xi plus 1. The distance between these 2 points are smaller than 10
Yeah.
to the power of -4. So
Times the distance. Yeah.
yeah, let's see.
Yeah, and the result shows for the points, or for all the points they choose, a continuous path exists. I think they test around
How many points?
1,000 images.
One
Around
1,000. So 1,000 images means that every pair, so they're close to one. Is that 1 million pair?
Sorry, I don't
The
remember the exact.
point is that so let me repeat. The point is that there's 1,000 points.
Yeah.
If there's 1,000 points, it means there's close to the magnitude of the pair. The number of pairs is close to 1. It's about 1 million, right? 1 million pair. So because your past search evidence happens or is applied for a pair of points instead of 1 point.
Yeah,
Right? So here, so you think that they applied on 1,000 points. This means that they almost work on 500,000 pairs to see.
Actually, I'm not so sure. I just remember 1,000 this number, but I'm
No,
not.
You're not sure it's 1,000 pair or 1,000 points.
Yeah, I kind of forget, but later I can check this. Oh, 1,000 pairs of points are considered. Sorry. Yeah. And then further, they ask a question about the shape of the path. They want to know if the path is straight or curved. So in order to find out this, they define dp. So dp is the ratio between the distance of the path we find and the straight line between p0 and p(n+1).
Sorry, DP is
P is the anchor point. Remember, we start from x1 and then p0, p1.
PI is the anchor point.
Yeah.
PI is the anchor point. So it's supposed to be larger, right? So the DP is supposed to be a value larger than 1. Right.
Yeah, and they said if dp is close to 1, then the path is almost straight, and if dp is large, then the path is curved.
By the way, so here, so in their experiment, the x or the p, anyway, x and p are in the same space, right?
Input space. They say input space. For example, like
Yeah,
Sivat.
they're in the input space. So I'm asking that so how do they define input space? They just use the image directly, or they're using
Directly.
the
Because
image directly? Okay. So
yeah,
they're not looking to, for example, the gap layer or the representation layer.
no. Just the input space. Like Sivat 10, it has 3072 dimensions. Then the input space should be 3072 dimensions.
Okay.
Yeah. And the definition of DP is the ratio between the distance of the path they found and divided by the straight line.
So what's the point of defining such a DP?
Yeah, so if DP is close to 1, then the path they
Yeah,
found.
okay. So okay, I somehow got it. So if DP is, if most DP sorry, is close to 1, it means that the space is more continuous.
The space is more continuous.
More like somehow more like this. Suppose, let me write down something. Suppose we have a space like this.
Oh yeah, yes.
So in
Yeah,
this case, the DP will be much
Yeah.
bigger than 1.
yeah.
If we have a space look like this, so the DP is very close to 1.
Yeah.
Okay.
And then the result. The result shows that DP is close to 1 plus 10 to the power of -4. So the path is only a slight deviation from the straight path. That shows almost if you wanna find a path between any 2 points, then the path is almost straight. So that's the result. And then further, they ask this question: does this tells that the classification regions are convex, just like the image you draw before? And the method they use is they use random convex combination of X from the same class and check if that combination is still belong to that class. Did you get the idea? And examine the
It's not a puzzle here. So but I'm still digesting.
which one? Which part?
I'm still digesting the shape of this, the shape of the space, the shape of the space. So for now, you're saying that when we finish training the model, and the model is more like a, so I mean the space of each class are very tight and very connected. Yeah, but they didn't. How many models have they tried?
I think ResNet and GoogleNet and
They just
And-
they just try the state of the art. Maybe I'm saying maybe. So such a feature is a good indicator that the model is well trained, right? Maybe, for example, suppose the shape space looks like this or looks like this. So they're quite intertwined with each other. It means that the model, does that mean that the model is more vulnerable because any perturbations across the regions, it may be, it's more like unstable. It's more unstable. For example, when we read the history, when the territory of a country is separated, it means that the countries may not so stable, or the control of the country over some territory is not so smooth. So does the idea still apply on the same on a deep learning model? So for example, so now you're saying that we're using ImageNet or using GoogleNet, and because these two models are very well trained and will be well used by a lot of the researchers, so they showing that such a, so the classification regions is very well connected. But I'm asking the questions. Maybe the answer may not be correct. So I have a hypothesis that whether the highly connected classical region is an indicator for the quality of the classification model, and whether the intertrend regions is the best map of the model.
We still have one last question. Maybe we can go through this question and
Maybe we come back. I just my imagination is just to fly a bit. So let's come back. Let's graduate to your slides. So the method. I'm saying the method. So you're saying that you want to see now we have already know that the classical regions are very interconnected or very connected. So the question is whether these regions are convex, right? So the feature of convex is that and if we want to define the convex shape or convex regions, then what is the measurement? What is the measurement? Is the measurement of the loss function?
No, they just randomly combine some x, add them together and check if the combination is still inside the class. For example, we can combine three.
Convex, so how do you define a convex combination? Is it affine combinations or it is just a linear combinations, 1 to x?
Linear, I think it's linear combination. For example, if we have x1 and x2 and x3, then the new combinations should be x1 plus x2 plus x3 divided by 3. And we check if this combination is still inside or belong to the same class.
The answer is supposed to be yes, right?
Yeah, and then if yes, then we can tell that classification regions are convex. If not, then it's not.
Why this can lead us to a convex conclusion? So
because the definition of convex set is any affine transformation of 2 points inside the convex set. Slope belongs to the convex set.
Okay.
Yeah, and then they examine the probability that this combination still belongs to the class, and then the result. Where is my mouse? Oh. And then on the left is the result. The x-axis represents k, or the number of points we are combining together, and the y-axis represents the probability. So from here we can see if k equals to 2, then the probability is over 80%, so it's high. But if we add, if the k becomes larger, for example, if it equals to 8, then the probability that all combination belongs to the same region quickly drop below 0.3.
Below, not 0 point, right? Just close to 20.
20%, 30%.
I think the drop is linear, right? The trend of dropping is linear.
So they propose that even though there might be a nearly straight line between any 2 points, but there are some regions inside that belongs to other class.
But definitely it cannot be represented in a 2-dimensional space, right?
So on the right is their imagination on how the classification region should look like, only for the red point.
There's a lot of hole. There's a lot of hole in between.
Yeah.
Okay, so this small hole means unstableness, right? So that means let me write something. So given that, so if there is a fully connected region, or if the region is full, then this line is supposed to be straight, right?
Yeah.
And so this region, for example, if suppose the combination is supposed to be here. If we have a linear combinations, suppose this A, B, and E, and we have combination of x here, and this hole. These holes means adversary samples, or Because
I'm not sure.
there-
I'm not even sure if this sample looks like images or it looks like a normal image, right? If you just randomly combine any 3 or 4 or even 8 images and you add them together, then what would it look like? It might look like nothing. I'm not sure.
Yeah, so but we once, so that means, does that mean that the combination of the two images is still a reasonable images, but the combination of 3 or 4 images, it becomes less likely to be, or do you think the combination, the linear combinations of multiple images not lie on the manifold anymore?
Yeah, I think that's my point. It might.
But we haven't tried before, tried it ourselves, right? And also, so once you mentioned that we try to use a mixed up approach to generate the boundary points. And so with this paper, it provides us justification for our method, right? So it means that the linear combinations, the linear combination of two images have a more somehow be justified in.
But that is I have a question here. For example, in their example, here, for example, this is from their paper, and you can see the P2 lines in the middle. The image is blurred, and
But the model still believe, yeah. So here, okay. So I got your point. Your point is that even if some points in the middle, even if there's a continuous curve between the starting and the ending point, but the anchor point may still not lie on the manifold.
yeah,
So that is your point.
that's my question.
Okay, so but that is okay, because when we are applying our approach to generating the boundary points, we require that there's a minimum perturbation, right?
Yeah.
Perturbation, so we can still believe that it's on the manifold form. Because how to define the manifold, or the definition of the manifold is very ambiguous. It's very hard to say.
So yeah, that's the part where they investigate the property of classification region. And then further, they wanted to investigate the curvature of the decision boundary. So a little bit introduction to the curvature. For example, on the left image, for any line, curved line, we can randomly find a point, let's say P. And then around P, we can draw a circle according to its curvature. And then the radius, and then we define the radius as R. And then the curvature.
So let me repeat it. So we have a curve. We have a curve, and how?
On the right, left image, for example.
Understand. So there is a curve, and then you find a point on the curve, and we do a tangent. We have a tangent line and have a vector there.
Yeah.
And how? And this curve is dp, right? Is I'm trying to connecting your slides with your previous slides. So the question I'm asking is that this is a starting point and this is an ending point, and this curve is a continuous line between X.
No, that's the totally different part.
Okay, it's totally different. Okay, that have nothing to do with the previous slide.
No.
And this curve is
Decision boundary. Decision boundary.
The decision boundary. All right, I see.
Well, no, I'm just telling what the curvature mean here. Like you can find a point P lie on a line, and you can draw a circle based on the curvature, and define the radius of the circle as R. And then the curvature should the value of curvature should be 1/R, in a sense that if the line is straight, then the R should be very large, right? And and the curvature should be close to 0. And if R is small, then the curvature is large. And that means the line around P is highly curved.
So I'm trying to digest in your formula here.
And
So,
then
please, maybe you can keep going first.
and then for the deep neural network, first for any given image X, they can do the adversarial attack and find the minimum perturbation. And after that, X plus the perturbation, we denote it as Z. So Z lies in the decision boundary. Let's say on the image on the right.
Yes.
And then the curvature along, it's the tangent space. If the Z is from D-dimensional space, then the tangent space should be D minus 1 dimension. And
right. So here, so Z is beta points, right? So which Z is Z is an adversary.
Adversarial point.
Okay.
And V is the tangent vector V from the tangent space. And the curvature is defined as V, the transpose of V times the Hessian matrix HF and times V. And
what is F?
F is
A derivative.
the FIZ minus FJZ, remember?
I didn't try to search my memory. I didn't.
FC is FIZ minus FJZ.
All right, got it.
Mm.
Hey, by the way, so so can you still stay in these slides? So, sorry, can you go back to the previous slide?
This one?
The big F, the definition, yeah, the definition of big F. So FIZ minus FJZ. So it depends. That means that for every dimension on the FZ, so FZ is the result of FZ is an n-dimensional vector, right?
It's a value because FIZ.
Sorry.
Let's say we output. If we have 10 class.
FZ is scalar. FZ is scalar, right?
And
let me see. Sorry, the FZ is an n-dimensional space, n-dimensional vector, right?
Yeah, and Fi should be the score for the I class and J.
Yeah, so these I and J is for any Z and J, and for for this definition is for any I and J, or for as long as we need exist one I and J satisfy such a condition.
I think when they talk about it, it's a binary classification problem, and later when they run the experiment on CVPR, it's one class over the rest of other class.
Okay, well, please remind me on which conference is this paper published?
CVPR.
CVPR, okay. So it's very theoretical, but it's an empirical study, right? It's not a theoretical.
But still in their paper, they have some mathematical equation formula, something.
Okay. Assume that it's a binary classification. Okay. So
yeah. And the curvature is defined as this. Maybe we can just remember this. And then they try to find the principal curvature correspond to the non-zero eigenvalues of the matrix. I think the process of finding the principal curvature is very similar to the PCA principal component analysis. So in the tangent space, first they find a tangent vector V that can maximize the curvature and then record this, let's say V1. And then they find V2 that is orthogonal to V1 and again have the second largest curvature. And then go on.
let me digest. So the curvature here is that giving so suppose that because giving the v here, so giving a z, the v is defined. The v is
A tangent vector.
I understand. So that means the v can be derived from z, right?
No. For example, on the right.
V is a tangent vector on z of the boundaries. Also,
Oh yeah.
so suppose giving a z and the classification function f, and the v can be derived from here. So by using g here, so it is possible to derive from v, right? So the curvature is basically measures how curved the shape on the boundary points.
Yeah.
Boundary point, right? So this is basically what we did trying to evaluate. And this is the scalar point, right? This is scalar point or
Which one? Z.
okay, the k.
K, yeah, K is the scalar. The curvature is a value. Yeah. And the principal curvature should be, each principal curvature should correspond to one.
So here I still have a question. So when we have to say eigenvectors or eigenvalues, means that we still need a vector, right? So the eigenvector and eigenvalues apply on a vector. So we choosing the k most important dimensions for vectors. It's more like we will have a dimension reduction technique there. But since the curvature has already been scalars, and how do we apply the principal component analysis on the curvatures, or the principal dimension analysis is on FV?
FZ is orthogonal to the tangent space. So from my personal understanding is that the derivative of f with respect to z should denote the curve. And then again, this curve, we calculate the derivative of the curve with respect to z should be the changing rate of the curve. I'm not sure if it's
I somehow got a maybe partial your so let me say my understanding, but it may not be correct. So when we have fc, so fc is supposed to be but anyway, f itself is the vector scalar, right? F itself is scalar, and z itself is the birth rate. But anyway, so but the derivative of f over z,
yeah,
it is a vector, right?
Yeah, and then again it's the matrix.
Yeah, so given these vectors, when we have these vectors, we can apply the. But anyway, this vector represents the curvature, right? How can represent the curvature, but it contains more information than such a KZV section. So when we have such vectors, we can apply the principal component analysis on these vectors, and
this vector, the matrix.
Where the matrix?
Hessian matrix. So
what is Hessian matrix?
Huh?
What is the Hessian matrix?
When you calculate the derivative of f with respect to z, the outcome should have the same shape with z, right?
Yeah.
And then again, you calculate the derivative of this vector with respect to z again, then
that means it's 2 degrees derivative.
Yeah.
So then how many times do we need to apply on these? So we have 3. So the Hankel vector. So this one is n times 1, right? Right. The vector is n times 1, right? So when we further apply the derivative But further apply the derivative, it was still another second. Suppose it's the second one. Suppose this is the first degree of derivative, and this is the second degree. This is n plus one again. And how many times do we need to apply?
Twice, only twice.
How many? Twice, only twice.
So I think first it should look like f with respect to, let's say, Z1. And then it's
This is the first degree. Yeah, this is the first degree.
yeah, and like this. And for the Hessian matrix, it should look like f square to let's say Z1 square.
Wait, Z1, Z2. Why there will be Z1, Z2? There's only one Z, right?
Z is a high dimensional.
Yeah, Z is a adversary sample.
Yeah, but let's say if it has 3,000 dimension, then Z1 should be the first dimension and Z2 is the,
Z1 is the first dimension of Z.
yeah, and then the second should be,
Yeah, I'm saying that. So I'm asking, or what I'm asking is that what is the size or what is the shape of HF?
then it's n times.
N times N.
So that's what where you can apply the eigen decomposition to find the eigenvalues.
Okay.
Yeah.
Okay, thanks. Let's keep going on.
And then they wanted to examine the principal curvature. So like the distribution of the values, they want to see that. So for each image, they add a perturbation to get Z, which lies in the decision boundary. And when you get Z, you can get a Hessian matrix like we talked about before and calculate the principal curvature value. So if Z has 3,072 dimension, then we should have 3,071 principal curvature, right? Just each corresponded to one eigenvector. And then here is the result. On the images, the average principal curvature values of 1,000 images. But here the x-axis denoted component or the principal curvature, and y-axis denoted the value. So from this picture, they show that in most direction, the principal curvature is close to 0. Then that means the decision boundary in those directions is almost flat. Only a small number of them is negative or positive. And further, they found that the principal curvature profile is asymmetric, especially the negative part is larger than the positive part. That's true.
So may I further questions between positive and negative? So what does it mean to be positive and negative?
Positive mean, that just means the direction. If the curvature like on the right,
the two binary
like on the, I mean
like binary application, so the positive is towards one side and the negative towards the other side.
Yeah, like that's the Z. And if the direction points to this way, then it's positive. And if it points to this way, it's
so it means that the boundary is more lean towards one side because it's an asymmetric shape. And the maximum value of the negative value is minus 0.04. Contrast to the positive side is less than 0.03.
Yeah.
So the shape is more towards the
negative part. And Yeah.
Okay, but the flat does not means wide, right? So wide, what I mean wide. So given a boundary B, so the B is supposed to be, okay, if it's flat, it means that be wide. Does it mean to be wide?
You mean did they provide explanations on why most directions
Yeah,
flat?
but somehow means the flat means be wide. So the boundary between two classification boundaries is supposed to be wide, right?
Why?
Think about it. So suppose this is classification region 1, and this is classification region 2. So if the boundary point will place here, it's definitely in this region, right?
Oh,
Right.
I'm not so sure what.
Well, you can think about it. So the curvature trace is basically calculated from the derivative. All right.
Calculate the derivative.
The curvature trace calculated from derivative. If all the derivative if the derivative is zeros, then the curvature will be 0. All right. Can we go back to the previous slide? In the previous slide? Yeah, so that means if the derivative and this one, if these vectors all zeros, so the curvature will be 0, right?
That depends on
derivative if the derivative is zeros and the curvature will be zeros. But otherwise there will be some perturbations and the positive, another positive or negative. Right. So then I'm saying that so if the boundary between two classification regions is very wide, so it's go to here, then for every direction they have, they're supposed to be 0, right?
let me digest. You mean if the classification boundary is wide, then
just raise a small metaphor here. So these are two regions. And only the boundary and only the boundary between in here it will have a
but in their case, they have a very strict requirement that FZ needs to be equals to 0. Then why would it?
It's okay. FZ could be equal to 0, but because the point on here and here and here, they are all 0. They're all 0, right?
Oh.
And the difference is that their HF will be different. And if the boundary is let me write some purpose here, is in these regions, and the HF will be 0. But the boundary is the boundary here in this region boundaries, and the HF will be have something. Right. So I just have a hypothesis and just put it to discussion. Is that giving a point if the boundary point is wide, and the boundary in these regions, it will have a curvature of 0.
I think their point is the boundary loop is straight and here is Z. And then this part is classified as one class and the other part classified instead of like it look.
No, I understand. So I'm saying that if the boundary is strictly straight, the curvature will be 0, right? But what if the boundaries? What if is a wide boundary between classification 1 and classification 2, and the boundary located in these regions, and that means any derivative, any directions from these boundary points will always be 0, right? Will always be 0. In this case, calculation.
Why would that? Why? Because
HF will be 0. The HF is a derivative for F over Z, right? The derivative of f over z.
twice.
Maybe you can skip this point, but we can leave the hypothesis. We can leave a hypothesis that might be so. So here is the most. I mean, the most curvature will be all zero. That implies were there an implication that the boundary between two classes is flat? Is there an implication? I'm not sure, but you can.
Later they provide they investigated what's the difference between those flat direction and those curved direction.
Okay.
Yeah, later. Yeah, and then they're asking, these directions first is they want to know, are these directions shared across different data points? They mean that in this slice, they found that some directions is curved, some directions are curved and some directions are flat. They want to know if this direction shared across different data points. If they find, for example, if they are given more unseen samples, do those unseen samples still share those direction? So what they do is first they use 100 training samples to compute the largest principal directions. So they should get 100 direction, and then they merge those directions into a matrix M. And then they estimated the common curved direction as the M largest singular vectors of M. So basically they propose U1 to UM as some curved direction. And then they evaluated the curvature of the decision boundary in such directions for any point Z, any unseen point Z from the validation set using this formula. So UI is given, but Z is from unseen data. I think the top part means the curvature in direction corresponds to direction UI, and then they divided the expected curvature for point Z. And if rho IZ is close to, let me see.
Would be 1, right? So
Yeah. If it's close to 1.
60%. Connected to LICT
Oh, sorry.
HC75G03.
If pi IC is larger than 1, then that means UI is a direction that the second let me rephrase my word. If rho I is close to 1, then that means they don't share this direction, and if it's larger than 1, then that means this direction is curved for most unseen data.
okay.
Yeah. And then this is the result for most of the data. The average of rho IZ is larger than 2, or even some 100 of them is larger than 4. So this proves that these directions are shared across different data points.
So I didn't get it. The logical chain. You're saying that if the rho I is equal to 1, it means they share, right? But now
it's close to, if
to 1,
larger than 1, then that means they shared
Go back to the formula and I'll try to recap the formula.
Like, for example, oh, sorry.
So it is a curvature. So here the curvature of
This part is the average value of curvature for sample Z. And this part, the top part, is the curvature corresponds to direction UI. And they want to show for the direction UI, the curvature should be above the average, right? So it should be larger than 1.
So what if the average curvature is 0? So it'll be very, very large, right? But the average curvature may not be 0.
They want to know the relative, how relatively curved is the decision boundary in direction UI.
Okay.
Yeah. So yeah. So basically, this result shows that for unseen data, they do share those directions. And then another finding is that those directions they found are also tightly connected with the sensitivity of the classifier to perturbation. So that means they found out when you do an adversarial attack, if you perturb the image in those directions, it's more sensitive. So you are more likely to change the label. However, for those directions that are orthogonal to the direction we found earlier, then the classifier, the prediction is more, not say robust, but didn't change much. So how did I found this? Is first they construct a subspace S contains 200 direction using the method we mentioned previously. And then they compare the accuracy of C-button dataset when add perturbations in space S and orthogonal S. And this is the successful rate. So the x-axis denoted the perturbation, the size of perturbation, and the y-axis means the misclassification rate. So when they apply the noise in same magnitude, the noise in S have a higher misclassification rate, means the classifier is more sensitive in those directions.
So any further interpretations on these phenomena? So the data independent directions. And basically these directions are the pixels, right?
Yeah, it's the pixel.
And that means for every samples, as long as we perturbate along those kind of images, it will make the classification, make the classifiers more sensitive.
Yeah. That's their conclusion.
And a further interpretation, just wanted. What from your point of, do you think what we can think about that based on these conclusions?
Personally, I think maybe I don't know, because it's pixel and
yeah, so if it is the representation layers, it means that certain features play a more important role.
Yeah.
But it's pixels, and also even pixels, they have such a direction. So maybe we can keep these questions. Let's keep going on.
Yeah. And then another experiment is when they do perturbations to the images, there are 4 kinds of perturbation: random, adversarial, and x2 minus 1 just means they do convex combination of images, and the last one is gradient of X. So there are 4 kinds of perturbations. And the number shows they project those perturbations into the space S. And adversarial perturbations have higher proportion in those in space S. So they are saying that adversarial attack are stronger than the other 3 type of perturbation.
That's not a surprise, right?
Yeah, and it's not surprise.
Mhm.
That means the adversarial attack did learn something about those direction, maybe.
Okay.
And the last part is like, remember before we talked about the asymmetric property of the principal curvature. So in this section, they want to show this asymmetric property can help researcher to detect adversarial samples. First, to define the average of the principal curvature, they just add them up and divide it by d-1. And then first they do an experiment to show that for original samples, the average of principal curvature almost all of them larger than 1 for 2 neural network architecture. And for perturbation samples, the average principal curvature is less than 0. And yeah.
Please.
And later they also suggest possible images like the perturbate images might stay in the red region, and normal images like X might stay in the normal region, and the curvature should look like this. And then they use this property as a threshold to detect adversarial samples. And in practice, I don't think they set the threshold to be 0, might be some t. And here is the comparison of, on the left is the comparison for different neural network architecture, and on the right is they compare different magnitude of perturbations. So it's just AUC curve. The y-axis means the true positive, and x-axis means the false positive. So they show that this property can be used as, say, a method to detect adversarial samples.
Will, can you go back? So I somehow lost the property details. So the property is that giving the asynchron, you mean the asymmetry property?
For each image, they can calculate the principal curvature, and then they can
apply the random noise, or they perturbate along this dimension.
And then they can calculate the average of the principal curvature. So for each image, we should have one value, one scalar. And they found out for the original samples, this value is larger than 0. For LeanNet, it's 97% true. And for the other NUS is 94% true. So further, they use this property to detect adversarial samples.
I'm trying to link up all these clues here. You can keep going on. Huh?
So basically, that's all.
That's all.
Yeah, that's all.
So let's recap it. So go back to the last slide.
This one?
The last slide, your conclusion.
Oh,
So the takeaway is that the regions are very connected.
for each class.
But does this argument or this statement contribute to any of the finding of the principal curvatures? There's nothing. How does it do they relate it? The classification region
No,
connection.
they are not related.
Yeah, but why they put it? Why these two contents are put into the same paper?
In the introduction part, they said they
Hmm.
investigated the geometric property for both classification regions and decision boundaries. So I guess they just put them into two sections.
And
And for the decision boundary,
their point is that so since they want to investigating whether there's a decision boundary inside each classification regions, if not, they can just look into the boundary. They just need to search the boundary between region. Means the inter-region, the boundary is only existing the inter-region relations instead of the inner region relation. Am I correct? Maybe not, because getting these boundaries, we can still getting the definition of boundary, they can still decide the shape does not contribute anything in the curve. Let's continue. The decision boundary curve in the same direction.
mostly flat. And then further they use this property. Oh no, they first show that the curve directions are much more sensitive to adversarial attack. And last, they use the asymmetric property to detect adversarial samples.
So I'm just curious about whether, because they are looking into the pixel level, right? Is that possible we calculate the curvature on the representation layer? So that would be more explainable, right?
Yeah, I would say yes.
And also the directions. But for the adversarial samples, but basically this paper is not that a CV paper. It's not that a CV paper. It's more looking to the theoretical or empirical analysis on the findings. Maybe I think Wang Chao's work can write in such a way, and we can got a chance.
Yeah, maybe, yeah.
Yeah, let's talk more on this Wednesday. So I think as far as I can see, I can only get these information from your report here. Maybe these contents will be dived in. I will actually rethink about these papers. And from your point, do you think this paper can link to your research? Any contributions to your research, the boundary visualizations? And maybe for example, I don't know, but just think on the fly. So that for the, so we know that for example, for the representation layers, for some dimension, it is have a zero curvature. So it might not be the interested dimension we care about. For example, if we conduct the dimension reductions, we might focus more on the dimensions with positive or negative curvature, or not really, actually, not really. So, yeah, curvature and adversaries. Okay, maybe we can talk more on our regular meetings.
I was thinking if maybe we can like move the meeting next week to Friday. Would that be okay? Because if I had exam on Tuesday, then
Friday, right? So Friday night we probably have a deadline. Maybe the Saturday morning.
Saturday morning. Okay, yeah.
Okay.
Yeah.
Okay. Try our best on the events. Yeah. Okay. Thanks everyone. Let's call it a day. Bye.